Hello everyone, I am excited to dive into our exploration of Twitter sentiment analysis using cutting edge natural language processing techniques. Today I will be presenting our project on Twitter sentiment analysis using natural language processing. The goal of this project was to analyze the sentiment of tweets, whether they are positive, negative, or neutral, and to explore the effectiveness of different machine learning models throughout the task. Project Overview. Let's begin with an overview of the project. Our main objective was to pre-process the textual data to make it suitable for machine learning models, build and compare different models, including traditional classifiers, autoencoders, and evaluate their performance to draw conclusions on their effectiveness in the sentiment classification. Dataset description. The dataset used for this project consists of tweets from the Twitter. We divided the dataset into training dataset, Twitter underscore training.csv, and validation dataset, Twitter underscore validation.csv. Each tweet in the dataset is labeled with one of the three sentiment categories: positive, negative, or neutral. Along with the text, the dataset includes metadata such as tweets ID and timestamps. Pre-processing steps. Moving on to the pre-processing steps, we started with text cleaning. This involved converting all text to lowercase, removing punctuations, stop words like the or is, and numbers that do not contribute to the sentiment analysis. We then tokenize the text using Spaces Encore Web Large Model, which break down sentences into words or tokens. Lemmatization was performed to convert words to the base form, such as converting run to running, which helps reduce the vocabulary size and improve model's accuracy. Finally, the text data was vectorized using TF-IDF or term frequency inverse document frequency, which weights the importance of words based on their frequency in the document relative to their frequency in the entire dataset. This is the function for the text cleaning and the vectorization using TF-IDF vectorizer. Model architecture. First is random forest classifier. Let's now discuss the models we use, starting with the random forest classifier. This is an ensembling learning method that constructs multiple decision trees during training. Each tree is trained on a random subset of the data, and final prediction is made by averaging the prediction of all trees. This method is particularly robust to overfitting, especially when dealing with high-dimensional data like text. Random forest is a powerful model for classification tasks as it captures complex interactions between features and can handle large amounts of data efficiently. Next is multinomial naive Bayes. The next model, which is a probabilistic learning method, often used in a text classification due to its simplicity and efficiency. This model is based on Bayes' theorem and assumes that the features, in this case words, are conditionally dependent given to the class. While this assumption is rarely true in practice, naive Bayes performs surprisingly well in text classification tasks. It is particularly effective when dealing with large number of features, as it handles high dimensionality of textual data with an easy. Next is autoencoders. Lastly, we experimented with autoencoders, which are neural networks designed to efficiently code of the input data. The architecture consists of an encoder that compresses the input data into a lower dimensional space or latent space, and a decoder that reconstructs the input from the compressed representations. In our project, autoencoders were used to learn compressed representation of tweets. These representations could be then fed into the traditional classifiers or used for anomaly detection, such as identifying outlier sentiments that do not fall within the usual patterns. We experimented with simple feed-forward autoencoders and potentially more complex architectures like convolutional autoencoders. This is the code for the model 1, random forest, second, naive Bayes, and third is autoencoder. Then we tried the hyperparameter settings which used for the models. For random forest, we set the number of estimators to 100, allowing the model to grow 100 trees, and we did not restrict the depth of the trees, letting them grow to their full potential. For the naive Bayes model, we use an alpha value of 1.0, which serves as a smoothing parameter to handle zero probabilities in the data. The autoencoders were configured with progressively reducing encoding layers, that is 128, 64 and 32 units, and mirrored the decoder layers. We then use ReLU activation function for the hidden layers and sigmoid for the output layer, optimizing the network using the Adam optimizer with a learning rate of 0.001. For the evaluation result, we evaluated the models using standard metrics such as accuracy, precision, recall, and F1 score. The random forest model had achieved an accuracy of 69.7% with a precision of 71.8%, recall of 69.7%, and F1 score of 68.9%. While the multinomial naive Bayes model had an accuracy of 61.65%, precision of 72.3%, recall of 64.65%, and an F1 score of 61.45%. The performance of the autoencoder was measured differently, using the average reconstruction error. The autoencoder achieved an average reconstruction error of 0.00175, and it detected 3 anomalies based on the reconstruction error, while holding the threshold of 0.00289. For the model comparison, the random forest generally outperformed the naive Bayes model in terms of precision, recall, and F1 score, making it the best choice for the sentiment classification task. The autoencoder's based approach provided an interesting alternative by compressing the data into a lower dimensional space, which not only reduced the computational complexity but also offered the ability to detect anomalies in sentiment. However, the autoencoder approach might require more computational resources and tuning for optimal performances. This is the analysis of the results of all three models. Conclusion and recommendations. In conclusion, the random forest classifier demonstrated superior performance and is recommended for similar text classification tasks, especially when accuracy and interpretability are key considerations. Autoencoders provide valuable insight by compressing the data and detecting anomalies, even though it was 3, which could be useful for specific applications like unsupervised sentiment analysis. Multinomial naive Bayes remains a strong contender in scenarios where computational efficiency is prioritized. For future works, we recommend experimenting with more advanced models such as transformers like BOT or robot, which have shown promise in recent NLP research. Additionally, augmenting the dataset with more diverse tweets and exploring additional features such as tweet metadata could further enhance the model's performances. These are the impacts of SPACY and the conclusions of the project. Thank you for your attention. I am open to any questions you may have.